Hello, my name is Mileva Radonjic, and today I will be presenting a research on permanent plugging and abandonment of wellbores, and really looking at how the nature would seal these wellbores. I would like to start this presentation, first of all, with the acknowledgements to thank Pierre Serrazi, who invited me to present at the CO2 GeoNet Forum, and to really express my deep sorrow that I'm not able to be there with you and spend some time in the beautiful city of Venice and enjoy the conversations and discussions that all of you will have. In addition, I also would like to thank all the people who contributed to this work, my former students, Cory Massion, Bamzi Visa, postdoc Marcia Shang, a student from Pitt, Yunxing Lu, and his advisor, Andrew Bunger, as well as Dustin Crandall from the NETL. The funding for the work that I will present today came from the National Academy of Science, Engineering, Medicine here in the US, specifically Gulf of Mexico program, also known as NASEM GRP. The project partners made this project really successful, so I would like to acknowledge them as well. SINTEF from Norway, University Texas of Austin, Louisiana State University, University of Pittsburgh, and of course my own university, Oklahoma State University. Finally, I would also like to appreciate the support, help, and commitment of all the lab members of our geomimicry and barrier material labs here at OSU. So, what is actually the wellbore system? As it states here, it really comprises of rocks, metals, and cements. And so the graphic here, a schematic on the right-hand side, is showing you how that looks in real life. And it shows both primary cement as well as the cement plug. Here on the left, there are three categories of points that are really important to distinguish. One of the, first of all, is cement failures. Second is factors that influence those failures, and then at the end, what are the solutions or options that we have to mitigate these. So the failures really fall into mechanical, chemical degradation, also debonding between these interfaces, and finally the increase in permeability, which is the ultimate a problem for any fluid sealing in the subsurface. So what are the main factors, you might ask, that are causing these problems? So in subsurface, we have various stresses, the earth stresses. There are also mechanical stresses that come from the operations. Sometimes they're induced by temperatures and pressures. There are also chemical attacks caused by very harsh subsurface fluids. Shrinkage of cement can be an issue, and of course various types of contaminations, both chemical and physical, that can happen during cement placement and later operations. So what are some of the solutions? First and foremost is improving chemical compatibility between cement or indeed any barrier materials that we engineer and place in subsurface. They need to be compatible with the subsurface. The reduction of porosity and permeability are always a goal. And finally, we also need to try and make these barrier materials less brittle and more on the ductile side. So if we look at the Earth and what are the most effective barrier materials in Earth's subsurface, shale or clay-rich type of rock is really what comes to mind. So if we look at a very simplified model of what shale is, as shown here with this graphic that was, I believe, initially proposed by Halliburton. Any shale can have inorganic and organic matrix. Within inorganic, we can have very fine nano size type of minerals, clays, and we can have more brittle, stronger type of materials such as quartz, calcite, feldspars, pyrite, and various other minerals. In organic matrix, we see kerogen, as well as over here on the right hand side, there can also be storage of various fluids, gas, oil, water. And for both inorganic and organic materials that make such rock, we do have presence of porosity. There are pores in organic matter and there are pores in inorganic matter, and they vary in size from easily observable micro porosity, micro fractures, to a very fine nano porosity that is typical of clays as well as kerogen. So to mimic the shale and adapt currently used Portland cement based materials, we decided to add something organic to it. That's graphene nanoplatelets in our case, carbon-based, ferrite, which is a material or a mineral rather that is very stable at temperatures and only starts to react at extremely high temperatures. And finally, olivine, which goes through conversion in presence of CO2-rich fluids, again at elevated temperatures, and it forms magnesium carbonate, which is a way of locking CO2 through mineralization. I will just skim through this slide. Basically on the left you have information on how we design these cement slurries, following again always protocols that are used by industry in all verification of cementing or cement-like materials. On the right hand side are the percentages of graphene, ferrite, and olivine we used in this study. So how comparable is graphene, or in our case graphene nanoplatelets, to the organic matter we observe in shales? Graphene is a relatively new material. It is a single sheet peeled from natural mineral graphite, and in case of our study we used material that was obtained from biological waste. So we did not have single sheets of graphene, but rather several of these sheets combined. Therefore, we call them graphene nanoplatelets. It's extremely strong material. It has also a high flexibility. It's very thin, therefore light. It's thermally and electrically conductive, and very importantly, it's hydrophobic and chemically resistant. So what does the graphene nanoplatelets do when mixed in cement slurry? As shown here in pictures, we can see these graphene nanoplatelets actually occupying the weakest part of cement, which are the pores, and therefore provides the reinforcement, and you will see later on that way they impact the mechanical property of cement, which would otherwise be very brittle on its own. The second mineral we investigated in this study as a potential candidate for enhancement of wellbore cement is zeolite called ferrite. It is highly crystalline porous material. It shows pozzolanic reactivity at high temperatures and very slow reaction at temperatures below this. It has therefore potential for self-healing properties, as it stores moisture that can later be released during presence of fractures and induced stresses, as well as if there is an increase in temperature. This material will react with any highly alkaline fluids such as calcium-rich cement pore water and provide the precipitation of calcium silicate hydrates. Do we have evidence for something like that? Yes, as you can see here in these pictures, even at relatively low temperatures of 90 C, which is what we used in our study, we did observe, when we looked at fractured surfaces, as shown here on the right-hand side, the so-called bridging effect that we believe is a result of presence of zeolite in this particular cement design. And perhaps the most relevant to this conference is how do we combat that negative impact of CO2 on any well-bore barrier materials, especially cements. So this is a study that was carried by Kellerman and Matter in 2008, and it shows that at specific temperatures and pressures, mineral olivine can actually be converted to magnesium carbonate. This is very well observed in nature at large scale, but obviously at geological time. So the goal here that my colleagues at Pittsburgh did, they used some olivine sand, they invaded it with CO2-rich brine, and they produced really nicely compacted, solidified magnesium carbonate. Well, to make that carbonation of olivine benefit cement, as it is not recommendable to actually mix olivine sand for pumping and other reasons into the wellbore, we produce some crushed particles of olivine, we mix it with cement, and the goal was to first see whether there is any reactivity between cement and these olivine particles. As shown here on the right hand side, we conducted a thorough chemical investigation using energy dispersive spectroscopy within scanning electron microscopy to investigate that, and there was really no evidence of reactivity. After several weeks, even months, these olivine particles remain intact. Therefore, our hypothesis is that these particles would be able to react with any invading CO2-rich brine, as shown on a previous slide, should cement ever be invaded by such fluids. So in all previous slides, we've shown some microstructural evidence and chemical evidence of how each of these three additions improve or enhance Portland cement as a wellbore material. Perhaps one of the most critical is also mechanical properties of these cements, and we tested these at reservoir temperatures and pressures. As you can see on this slide, in red, you see failure of neat Portland cement. That means no addition of anything else. The other colors that are shown here, graphene is shown in blue, ferrite is shown in yellow, and olivine is shown in green. The lighter the color, the lower the percentage, the darker the color, the higher the percentage of the additive added. So as you can see, we do in every of the material that we design, we do see improved properties. We see that not only like in the case of ferrite at 5 and 15%. The cement can withstand high load, but the failure is not so abrupt as in the case of graphene. We see more flexibility of this cement, which is really what we want. To further investigate the failure of these materials, we did X-ray microscopy so that we could look at the volume of these fractures and the nature of these fractures for each of the three designs and compare them to the neat cement. So here in green you see neat cement, for example, and you see at the bottom this chart shows you the volume of the fractures present after the failure. On the right hand side you see the same type of test for a graphene enhanced cement, and you can see that the volume of fractures produced after the failure are substantially smaller when compared to the neat cement. All the way on the right hand side you can see 4 CT images of each of these materials we've been talking about. Well, the first one on the top left is the Portland cement. As you can see, there are substantially higher volume of fractures in that one than in any of the other 3 designs. Again, this is highly desirable outcome. So in discussion, conclusion, and ongoing and future work, just to reiterate what I already presented, and that is that all of the 3 additives that we investigated, graphene nanoplatelets, olivine, and zeolite, when added to Portland cement, really improve mechanical properties of wellbore cement. Olivine microparticles are definitely potentially going to be able to prevent a negative impact of CO2 on wellbore cement by incorporating that CO2 into a newly formed magnesium carbonate, and therefore preventing any leakage and destruction of cement hydration products such as calcium hydroxide and calcium silicate hydrates. The other observation from this study is that zeolite would probably provide pozzolanic reactions at the higher temperatures, but also there is this potential for delayed response should there be any fracturing or invasion of other fluids. It can store some of the cement pore water and provide that towards the self-healing during the potential fracturing. Also, zeolites potentially could actually be used for uptake of heavy metals and toxic components that can sometimes be discharged over the years when that casing made of very heavy special alloys and heavy metals potentially can be discharged into the subsurface water. And our ongoing work is focused on now combining all these different additives, and the goal is to produce a nanocomposite. It will be based around Portland cement, but there will be substitutions with this as well as some other minerals such as silica and potentially limestone, all in an effort to produce wellbore barrier materials that are capable of withstanding much longer time service than what is initially required when we construct wellbores for production. And finally, I would like to thank you all for your attention and your time. If there are any questions, please do send them, or comments, requests for collaboration, I hope too. Please email me at mileva.radonjic@okstate.edu. And below are the 3 publications that came from this study that you can find online. Once again, thank you and ciao.